Hello, everyone. Thank you so much for being with us today. I'm Lucy of Sierra Circuits, and today I'm here for a very special webinar with Jonathan Riley, Technical Director at IoT Routers and M2M Gubbins. So like I said in the email invite and in the confirmation email, today's webinar is very special. It is not going to be the regular type of webinar we do, on PCB design and manufacturing. This is going to be a special presentation on space radiation. So all you have to do is sit back, relax, and enjoy. During the presentation, though, we are going to have a couple of quizzes. So at some point during the presentation, you will see a pop-up on your screen with a question and you can answer, and hopefully you get the right answer. So Jonathan and I, just a little bit of a background here. Jonathan and I met because he is one of the top members of our PCB community, Sierra Connect. So we started talking and he had a very interesting background in aerospace. And I thought, oh, do you want to do a webinar with us? And he said, yes, so here we are. Just a couple of words about Sierra Circuits for those who don't know us. We are a PCB manufacturer and assembler located in Silicon Valley. We do very high spec, high technical printed circuit boards, prototypes. And we are ITAR certified. We do mil spec. We do, medical, automotive, basically anything you need. Thank you so much, Jonathan, for doing this with us today. You have the floor.
Thank you, Lucy. Right, let's get started then. So here's what we're going to be looking at today. To begin with, we'll consider the 4 sources of space radiation, and then we'll look at what protects the Earth itself. We'll investigate the 3 key problems that electronic systems face because of the high-energy particle environment, and this breaks down to single event effects, and also we'll consider how do you test for that, and we'll think also about the total ionizing dose and total non-ionizing dose, and also how we can predict the system downtime as a consequence of space radiation. But before we jump in fully, we'll actually have the first one of our quizzes.
Okay,
So,
and here it comes. You should see it on your screen now. There you go. Okay, only a few seconds to answer.
okay, so Telstar 1 is probably best known as the first communications satellite to bring live TV signals from the United States across to Europe. Launched back in 1962, what I'd like to know is how long was it operational for? Was it 7 months, 3 years and 10 months, 11 years and 2 months, or is it still operational now?
Okay, shall we see what people say? And Paul. Well, okay, so it looks like most people got it right.
Yes, a mere 7 months. The backstory as to why that's the case might surprise you. The day before Telstar 1 was launched, the first of the high-altitude nuclear bomb tests took place, and that, of course, filled the environment with additional radioactivity in addition to that which is present normally because of the sun. So sadly, the poor thing only lasted a mere 7 months, and it was then to be the first of many. So let's have a look at the natural sources of space radiation. It comes down to four things. The solar wind. The solar wind is a constant emission of particles specifically from our sun. It comprises mostly of protons and electrons, although, as we shall see, there are many other things in it as well. The second contributor are the galactic cosmic rays. These are high energy particles, again, mostly protons, but again, including all manner of other things as well. And the typical sources of these are things like supernova explosions in distant parts of the galaxy, as well as the emissions from other stars, sort of more in our neighborhood, as you might say. So although they're called rays, they're not, they're particles. Sadly, the scientist who discovered them was faced with a dilemma. He knew something was happening. He knew it was coming from space. Is it particles or waves? And sadly, the guess was incorrect. The third, this is actually more something that modifies the contents of the solar wind. And that's solar flares. So when our sun has a solar flare, they typically last maybe a few minutes, perhaps a few hours at the most. But the particles that these events release are extremely high energy. And we can see that in terms of the speed that they have, which means that they might only take 20 to 30 minutes in traveling from the sun to Earth. Set that against the fact that light itself takes 8 minutes. So these particles are traveling at relativistic velocities, and thus, although they might be tiny, the effective mass they have is far, far larger than you may imagine. And the fourth contributor is a thing called a coronal mass ejection. You can see that in the little picture at the bottom with the arched loop on the side of the sun. That loop, however, is still nonetheless big enough to fit the Earth into it, maybe 10 or 12 times or so. So these are large features. The result of this is that is what will cause the emission of the largest number of particles, but the individual energies tend not to be anything like so high as for the solar flare, with the consequence their travel speed is around about 1,000 miles per hour, and it typically takes maybe 2 or 3 days after one of the CMEs before the particles start arriving here on Earth. So we have a little animation that shows the particles coming from the sun towards the Earth. And in a little while, we'll ask the question, is it quite like that or is it a bit different? Anyway, let's have a think about what the solar wind is actually comprised of. As we've said, it's mostly electrons and protons, or protons are hydrogen nuclei if you prefer. As far as the protons are concerned, these are the smallest and lightest of the positive charge carriers, but they are the ones that occur in the largest numbers. So 95% of the positive charge carriers coming to the Earth will be protons, mostly from our sun. A further 4% are helium nuclei, and the remaining 1% or so is literally everything else, up to and including uranium. You might wonder, what about neutrons? Well, they are present, but they're a lot less common than you may expect. The reason for this is that the neutron is only stable when it's within the nucleus of an atom. Take it out of the nucleus and it decays. It's got a typical half-life of just 15 minutes. So as you can appreciate, many of the ones that start from the sun never actually get here. They will have broken down into a proton, an electron, and an anti-electron neutrino. But the thing that's perhaps the most interesting is when you compare our sun and the particles that it emits to everything else from the rest of the cosmos all put together. And that's what the chart on the right is showing you. So the dashed line is linking together the data points showing each of the atoms for what our sun emits. And the solid line is showing you the same except for the rest of the cosmos. When you look at the difference, you find that given the fact that that scale is logarithmic, the number of hydrogens from the sun compared to that from the rest of the cosmos, it's only a factor of 10 different. And for the helium, it's less than that. When you look at things like lithium and beryllium, you've got 1,000,000 to 1 difference there between the amount coming from the cosmos being 1,000,000 times more than the amount coming from our sun. From this, we can conclude that actually our sun is a surprisingly benign star. Not to say it doesn't have its moments. Anyway, what about the Earth? Well, the Earth is shielded from space radiation. The magnetic field produced in the core of the Earth produces a magnetic field which interacts with the high energy charged particles. If you remember from physics, back when you were in high school, you'll remember that the moving of a charged particle within a magnetic field results in a force which is at right angles to both of the other two directions. And this ends up resulting in some of the particles being deflected and simply going back out into space, and others actually being captured. The ones that are captured are trapped in belts that we'll look at in a few moments. But one of the things you might find interesting is they don't simply move from North Pole to South Pole and then back again. They actually spiral. And as they get closer to the Earth, so they spiral faster because the magnetic flux is increasing as you get nearer to the source of magnetism. And so following this spiraling path, it will actually travel from one pole round to the other pole and then back approximately 12 times every second on average. So as far as things in space are concerned, these belts are a bit of a problem. As far as the Earth is concerned, this is great because much of the charged particle flux that's coming towards us never actually gets here. In addition to this, we also have an atmosphere. We define somewhat arbitrarily that the atmosphere is at an altitude of up to 100 kilometers or about 62 miles if you prefer. And beyond that is considered to be space. So at that point, the Earth finds that the charged particles coming in interact with the gases of the atmosphere, and so many of them are stopped from actually getting to the Earth. The few that do typically have very high energy levels, and these are what are detected in cloud chambers and other things. So let's have a look at the Van Allen belts. You've probably seen pictures like this before, where you have the sun providing the solar wind, and it notionally gives you the idea of there being a sort of a squished front edge and a drawn out back edge for the Van Allen belts themselves. Well, the European Space Agency actually set out to test if that's in fact the case, and that's what the Integral Radiation Environment Monitor experiment does. It's continuously monitoring from a satellite in a very peculiar elliptical orbit the particle concentrations as you go through the different parts of the belts. And they found that it's actually surprisingly symmetric, kind of like having a donut-shaped object, a toroid, surrounding the Earth. The highest concentration of particles is in the inner belt and less so for the outer belt. This is looking at the inner belt in a little bit more detail. Now, do bear in mind that the scale, once again, is logarithmic. So the outermost part of this is simply 1 centimeter squared per 1 particle per centimeter squared per second, increasing to 10, 100,000. And by the time you get to the million middle, you're around the 200,000 mark. So that's really quite a high concentration. Just for reference, you're probably wondering, well, what about astronauts? What about the International Space Station when you put someone up into this kind of environment? Well, actually, the green line here marks the position of the flight path of the ISS. It flies at an altitude of around about 400 kilometers, and it never goes further north or south than around about 50 degrees. And so it misses all of the worst of it. The red line is typical for a low Earth orbit satellite, and that's where the vast majority of these large constellations these days are being put. So as you can see, they do indeed cut through most of the higher concentrations in the inner Van Allen belt. So before we move on to look at the problems faced, we now have another of the quizzes. So Lucy, if you'd be so kind as to put the next quiz on the screen.
It is.
So thank you. In a typical low Earth orbit, roughly how long does one orbit of the Earth take? Is it 20 minutes, 100 minutes, 240 minutes, or 24 hours? I'll give you a moment to think about that. Typical low Earth orbit.
Okay, shall we see the answers?
Mm-hmm. And the answer is indeed about 100 minutes. So it means that those satellites in a LEO orbit are traveling around the Earth at something in the vicinity of 16 to 17,000 miles per hour. Right. So the three key problems as far as putting any kind of electronic system into this sort of an environment come down to three key factors. There are other variations and other things to consider as well, but this is really where we start when we think about how it influences the electronic systems. So SEE, or single event effects, these are what actually happens the moment a high energy particle strikes the active parts, usually, of an electronic system. It's caused mostly by positive ions. The reason for that is the electrons, by comparison, are far lighter and are therefore also more easily stopped by the metalwork of the spacecraft itself. So you tend to find that the outer part of the spacecraft builds up a net negative charge, and if it's not connected to the systems in the middle, they will build up a net positive charge. The end result is, if it's metal, it's got to be connected to something. You don't leave metal floating, because it will otherwise accumulate a charge of its own, and then it could well cause adverse things to happen. When the particles strike, it can result in just simply an immediate but momentary disruption which comes and goes, a transient. It can be worse than that. It can cause the thing to malfunction to the extent that it needs to be reset or possibly even power cycled. And the other possibility is it can result in the destruction of components for various different reasons. And we'll look at these later. That's how each and every one of the high energy particles affects it in the instant. But energy is also released, and you end up getting a buildup of radiation damage. And this is a cumulative thing, and we call it either total ionizing dose or total non-ionizing dose, depending on exactly what's happened and just what the effect has been. Total ionizing dose tends to be the one that we are normally more concerned about. It's the result of the ionizing radiation, typically the gamma photons that are released, and it produces a progressive, steady degradation of the component's ability to operate. And then at some point, it will typically go out of the manufacturer's specifications. And if it does that, we need to know, does it matter? And how is it going to affect the real system? So we'll see how we measure that a little later also. Total non-ionizing dose. This is principally a neutron thing, but not entirely so. It tends to cause displacement of atoms from their position within the crystal lattice. So the silicon wafer, the lattice that you have there, when you have high energy neutron hitting it, it can be displaced from its proper position, and it can become an interstitial atom, or it can actually be caused to split apart so that you end up with electron hole pairs, but that's not normally quite how it works. And we'll see what sorts of things are affected by these too. So let's have a look at single event effects. As we said, the simplest one of these is a single event transient. It's a temporary voltage spike. It can occur in analog or digital or RF circuits, and it's due to, as I say, the energy dumped by a high energy charged particle coming to a halt within the semiconductor fabric. These in and of themselves may not be too big an issue, but it depends. If it's part of a circuit that's monitoring, say, the status of a power supply, it could momentarily flag that the power supply has overloaded, in which case you may end up shutting the system down. So it was there, it was a temporary thing, but it was misinterpreted. So you get things like that. You can be making measurements of other aspects, and the ADC is hit and it creates a transient, and so you'll get an erroneous reading. So these are the kinds of things that can happen with that. Next, we have single event upsets. These are the changing of state, or a bit flip if you prefer to call it that, of register contents or memory cells. These normally only affect one register bit or one memory bit, but it depends on the angle of impact. So sometimes if it's part of a memory array, you could find that two adjacent memory bits are affected. They may not necessarily be in the same word, but they can cause this kind of an effect. If the word temporary there is making you wonder, it's temporary only in the sense that it can be reprogrammed back to the state it's supposed to be in. It's not that it makes the thing show the wrong value, but when you look at it later, it's resolved itself. It's a permanent change until the software or the system itself does something about it. Single event latch up, well, that's a destructive effect, or at least it can be destructive. It amounts to a short circuit between power and ground in a typical CMOS circuit. The reason behind this is that when you look at a typical output structure, you will see that you have a high side FET and a low side FET, but when you actually implement them on the silicon, you inadvertently create a parasitic structure behind it. And that parasitic structure takes the form of a thyristor or silicon controlled rectifier, call it what you will. Ordinarily, the control input to that is never activated. It's not connected to anything. But the passing through of a high energy charged particle can trigger it. And that is how you end up with the power to ground short. Unless the device is powered down, this sort of an effect is not going to resolve itself. And if it's not done quickly enough, some components will simply be destroyed because of the heat buildup as a result of this power to ground short within the die. Not all devices are affected. Some are particularly resistant to things like this. So silicon on insulator is a lovely technology and is almost never affected. So it varies. Single event burnout. Well, this is one of the things that is characteristic of MOSFETs, especially high power MOSFETs. And it's caused once again by excessive current flow causing the particular component location where the particle struck to heat up dramatically. It in essence amounts to a source to drain short and is generally not a good thing. SEFI, single event functional interrupt. That is where you have a single event upset in part of, say, a state machine or a control circuit. This is generally recoverable with either a reset or, if needs be, power cycling it. It does mean that when you create state machines for space, things like one-hot encoding is not normally a good plan because the high energy particle can introduce a second hot state and then your decoding goes hopelessly wrong. It can equally lose you the one hot state that you had if it flips that bit the opposite way. So there are certain things which really don't work well in that kind of environment. You have to be careful how you do things. And the last one that we'll talk about is single event gate rupture. This is where you have the oxide layer between the channel and the gate actually breaking down because the passage of the high energy charge particle through it caused a collection of electron hole pairs to be formed. With the presence of a potential difference between the gate and the channel, that encourages a flow of current. And once it's actually broken down, the thing doesn't work properly anymore. So again, SEGR is a permanent failure. Well, when we go testing for these things, we have some expectation of what we think we're going to see. We can look for transients, we can look for bits in registers being inadvertently set. So if you were testing a DAC, you might program its output to a particular state and then see, does it just happily stay at that value, or does the output, without you changing the programming, suddenly jump somewhere else? So again, we can do things like this. And when we do this, what we're interested in is not just what sorts of events take place, but to count each type of event so that we can then produce a graph like the one shown on the right. So on this graph, you have something called the linear energy transfer value, which is a measure of how much energy the particle is able to deposit in the die as it comes to a halt. And with this, the highest energy particles will always trip the thing, and so you have a plateau on the top. The lower particle energy may get you to a point where actually at a particular level of energy, the particles don't actually cause any effect at all. The flat top is defined as the limiting cross section. The point at which they no longer make any difference is called the let threshold. And by adding two more parameters, which just get termed W and S, we can then create an exponential function which describes the shape of the graph. Having that enables us to then do rate calculations, but we'll come on to that a little bit later on. How do we actually do it? It's split into two. The first testing that we would do is heavy ion testing. To do this, we have to expose the die, or there may be more than one die in the package, in which case we'll expose both of them or all of them if there's more than one. Once we've got the thing exposed, we can throw heavy ions at it. So typically this could be anything from something like maybe neon, which has a very low value of LET, something around about the 3 mark, up to xenon. It doesn't have to be a gas, it's just I like using the gases, they're easier to use. The xenon is actually accelerated so that each individual particle, when it hits, has an energy of 1.33 gigaelectron volts or thereabouts. In terms of how much energy it deposits in the silicon, that comes down to around about 60 MeV centimeters squared per milligram. In doing these tests, we're looking for both destructive and non-destructive effects, and the objective is to count how many of what we get and measure how much of an impact it makes. But if a part turns out to be sensitive to particles whose energy is below 15 MeV centimeters squared per milligram, then it becomes necessary to have to repeat the same process, but with protons. And for the protons, again, we will use various different particle energies up to around about 100, maybe 125 MeV. Again, we're looking for both destructive and non-destructive effects, although the vast majority at this lower overall energy level tend to be non-destructive. What do we need to test? Do we test everything? Not exactly. No. Some things like diodes and passive components, so your resistors, capacitors, inductors, for those, we're not really interested. It's integrated circuits, things like optocouplers and charge couple devices, so image capture systems, discrete transistors, yes, especially if they're power transistors, and the hybrid package devices where you have multiple things. Yes, we will test those too. For most things, it's just a one-step operation. You put the thing into the position in front of the beam, you turn on the beam, you see what effects occur, and that's fine for just about everything, but MOSFETs are a bit of a special case. So for those, we have to split it into two. The first part, we're interested in seeing if you have a bias applied between the drain and the source whilst the gate is in the off state, so the gate's at 0 volts, then we want to know, is there any increase in the leakage current as we use progressively higher energy charged particles? At the end of that test, what we then want to do is look to see has the gate structure been compromised, and so it's followed by something called the PIGS test, which is post-ionization gate stress test. And for that, the drain source voltage this time is set to 0, and we apply a progressively larger either positive or negative voltage to the gate with respect to the source. And ideally, in a perfect world, you'll take it up to the datasheet specification, which might be up to, say, 20 volts or minus 20 volts, and find it's fine. There's no additional flow of current beyond what we would expect, in which case it's passed the test. But these days, because of the past experience, we can sometimes cheat with the MOSFETs. We don't necessarily have to do single event testing if we derate the components. The downside is it's got to be derated really quite a lot. So your VDS has got to be reduced down to a mere 25%. So your 60 volt component you cannot use at greater than 15 volts. So as you can see, if you really want the best of the best, you're probably still going to have to go testing. So let's just have our third quiz question now, please, Lucy.
Okay, here you go.
So GPS satellites, to be able to perform their function, they have atomic clocks on board. What I'd like you to tell me is, are these clocks compensated in any way? And if so, how? So your choices are, nope, they're not compensated, they're atomic, they don't need calibration. Or is it B, relativistic effects due to the movement of the satellite around the Earth gives rise to the time not exactly being quite as we think, and so they've got to be calibrated to run fast? Or is it C, gravitation, that because it's lower when you're on the satellite than when you're on the surface of the Earth, does that affect it? Or is it answer D, it's both of these last two, both relativistic effects and gravitation? So take your pick.
Okay, shall we see the answers?
Yes, please. Okay, it's answer D. Both B and C are compensated for. Yes, the relativistic effects due to motion would mean the clock ought to be speeded up. And the effect due to gravitation, which is actually still a relativistic effect in another way, would say it should be slowed down because it would otherwise run fast in the reduced gravitational field of space. These two don't exactly cancel each other out. It turns out that gravitation is about 4 times stronger in terms of influencing things. So the net result is the atomic clocks on the positioning satellites are all deliberately calibrated on Earth to run slow so that when they are in flight in orbit, they're absolutely correct. Thank you. So we've looked at SEE. Let's have a look at total ionizing dose. As we've said, it causes a progressive degradation, and a part of it is due to the capturing of charge, not so much because of the charge of the individual particle that struck it, but because as that charged body zipped through the silicon wafer, the effect it had was that it created electron hole pairs. The electrons being much, much smaller and are therefore much more mobile are likely to get swept away. This means that you finish up having a net increase in the positive charge being held in the oxide layer of, say, your MOSFET. This therefore means that if it's a p-channel device, it's now harder to turn on. And so your gate threshold voltage progressively increases. For an n-channel device, it goes precisely the opposite way, and now they become harder to turn off. This sort of thing affects bipolars as well, and you find that things like the HFE are degraded with time. As far as ICs are concerned, you can see it first by noticing that the quiescent current that the device is operating at is just steadily creeping upwards. You may also be measuring the IO structure leakage currents as well, and you'd be quite likely to see that these are also worse. But it affects other things too, and by changing the gain, you also find that the other manifestations therefore are propagation delays through components typically increase. And so your nice little microcontroller, which down here on Earth you can run at 16 megahertz, the space version will only let you run it at 8 megahertz. So you'd expect some kind of derating. It's not to say that you can't design things to be fully tolerant of the environment, but if you're looking at upscreening off-the-shelf parts of the COTS components, then things like this, where you have to slow it down, is often the case. How do we actually do it? We put it in front of, normally it's a cobalt 60 gamma source. The reason that we tend to standardize on cobalt 60 is because it gives us gamma photons with a decent amount of energy, and it's in a sense fairly readily available because they're used in hospitals and many other places. It's not quite so esoteric as saying we want to use cesium or something. So it tends to be cobalt 60, and most of the standards have based themselves around that. What parts do we need to worry about? Well, Zener diodes, not normally, but only if you're using the Zener and have calibrated it and it's needed for a precision reference. Otherwise, Zeners, you don't worry. Other standard, mostly low power diodes, it's a no. Gallium-based components, so gallium arsenide devices, and the various other variations where you have other things in with it, indium, phosphorus, and such like. They are not a great worry most of the time, not unless it's going to be put into a radiation environment that's sort of 10 times higher than we would normally be thinking of for a typical low Earth orbit satellite. Other than that, all integrated circuits need to be tested. Your optocouplers and charge couple devices, for those, it's a definite yes. Transistors, actually, the very small ones, small signal devices, are not usually a great worry, but the power devices certainly. And again, stuff like passives, we're just not worried. It really doesn't matter about resistors, capacitors, inductors. Total non-ionizing dose. This is the one that we don't often have to worry about greatly, because as you look at the list of scenarios where it matters, you find that the one big yes is optocouplers and charge couple devices. So your imaging systems and the optocouplers. The reason for this is mostly because the damage that's induced results in the optical parts of the system becoming progressively more opaque. The color that it goes isn't necessarily that it just goes black, but either way, it's impeding the passage of light through them. And one of the commonest places of using optocouplers would be in power supplies for feedback, taking feedback from the isolated side back to the little switching controller. And so in that kind of an environment, having the component degrade, saying I'm seeing progressively less current, is not good. So for that sort of a situation, you just wouldn't use them. It's not to say that they don't exist, because they do. There are special space versions, and there are for very specialist applications, because they're not cheap. But there are ways around it. You may have seen pictures of crystals of things like quartz. You may have also seen pictures of what looks like a black piece of quartz. That can occur naturally. It's called smoky quartz, and it's radiation that's caused it. It's mostly when the high energy particles are interacting with the structure in such a way that it's exciting the impurities that are present within the materials, and it's causing them to take on a color. So that's why I say it doesn't necessarily have to be black. It could be other colors, but once again, it probably doesn't help. Last little thing to say regarding to just from a practical point of view, things like metals generally are resistant to TID and TNID effects, and for those, we really only need to worry when you're exposed to levels above 1 megarads. What about plastics? And especially plastics that are either surrounding cables or acting as the insulation within cables? Well, they vary. Things like PTFE are typically only good for about 75 kilorads max, whereas others like nylon are good for up to 300 kilorads. The thing that determines whether you'll get away with being able to use the PTFE at a 75 kilorad level is whether it's going to be flexed. Because one of the first things that happens is they become brittle. And if it becomes brittle and turns to a sort of a powder or dust, this doesn't really help with insulating things, and certainly in the RF world, it's undesirable. Anyway, let's move on. Measuring the effects. When it comes to having exposed the parts to the gamma source, we want to see how the components behave against the original manufacturer's data sheet. And so it becomes a statistical exercise, seeing what has actually happened. I don't propose going into this in detail. You can read about it at a later point, or ask questions if you so wish. But the thing that we normally aim for is to have a decent radiation design margin. This is the difference as a ratio between the amount to which we've tested the components to, the TID sensitivity, in relation to the TID that's going to be accumulated over the mission lifetime. The consequence of that is that if this radiation design margin is 2 or greater, then that's fine. We don't need to do any further testing. We don't need to do batch testing. If it's between 1.2 and 2, then we do need to do batch testing. And so this becomes radiation lot acceptance testing. And less than that, you need a very, very good reason to justify flying it. In the way that we can have shielding for a Faraday cage, keeping RF circuits from being interfered with or from emitting things and interfering other things, we can apply some kind of shielding to protect against too much accumulated total ionizing dose, or TNID. And it's density that matters. So the two materials that we tend to use if we go down this route are tantalum and tungsten. We mentioned system downtime. This is the other aspect that SEE gives us. Remember the Weibull curve? From that, we can actually do an integration over the orbit of the total number of particles of each energy and work out how often things are going to take place. The end result of this is that we aim to be able to give a customer a guarantee of what sort of system downtime they would expect. So for a relatively complex system, like say the frequency converters in a communications satellite, which are pretty critical to the objective of the satellite, then you might be allocated a target of maybe 20 to 30 parts per million. So per million seconds, you would be allowed to have the system be down for 20 to 30 seconds maximum. So it gives us a means of predicting system availability. And there is a bit of good news, and that is that some parts, as you have now seen, actually don't really matter too much, at least not in most of the environments that they're going to see in space. So your resistors, capacitors, inductors, connectors, they're all fine. Cables, well, we've already spoken about those, and it depends on what materials they're made of and whether you expect them to be flexed in use. And rigid PCBs are also not a worry. Flexi PCBs, especially if that bend is going to be exercised, then yes, they matter. And that basically brings us to just about the end of the presentation.
Shall we do the last quiz before we move on to the Q&A?
Okay. So we have one quick final question for the last quiz. True or false? Carbon dating is only possible because of high energy particles from space. What do you think? True or false?
Okay, let's see the results.
And the result is, it is indeed true. Put very, very briefly, high energy particles, say a proton hits an atom, the atom shatters, and as it releases part of its nucleons, you have low energy neutrons. When that hits a nitrogen molecule, it hits one of the atoms, is captured by the nucleus, but it's unstable, and so it emits not the neutron, but a proton. That is how carbon-14 is formed. That doesn't really want to stay bonded to the nitrogen, and so when it finds an oxygen molecule, it preferentially bonds with that, forming carbon dioxide. That's taken in by plants. Plants are taken in by herbivores. Herbivores and other things are taken in by everything else. Net result, everything that's been alive on the planet has carbon-14 in it. And so that means that for you and me, even today, we have carbon-14, and 1 in a million of the carbon atoms in you will be a carbon-14. And that gives us the basis for being able to date things.
Great. Thank you so much, Jonathan, for the presentation. Everyone, I will send you the slides and recording this afternoon. So now we can move on to the Q&A. And Jonathan, if you check the Q&A section, you will see there is one question already.
Indeed so. Right, okay. Clarifying the terminology between SPE, SEP, SEE, and CME. Right. And are they the same? They refer to different things. I have to admit, the first one, you've got me. SPE, I'm not familiar with. SEP is the terminology that gets used by Texas Instruments, and it's their space, and it's the enhanced, oh dear, I've forgotten what the P stands for. Thanks. Right. Okay, I'll come back to that in a moment, Terry. In that case, SEP could well mean something different. SEE is generally single event effects, and CME is coronal mass ejection. So coronal mass ejection and the solar particle events, which is another word for the solar flares, they're not the same thing. So the coronal mass ejection differs from a solar flare in that it produces, thanks, Terry. The solar flare produces very high energy particles in large quantities, but it's the fact that they are extremely high energy. The coronal mass ejection, the extreme is moved to the other word. So this time you have high energy particles in extremely large quantities. So that's the difference between the two. They're not the same, but they are caused by similar effects. So both of them are down to local magnetic disturbances in the in the polarity of the magnetic fields near the surface of the sun. The reason these things happens, I don't think is fully understood, but it's almost certainly related to the fact that unlike the Earth, where the polarity of which is the North Pole, which is the South Pole, is mostly fixed, and although it has reversed in times past, it tends not to be doing much at the moment. Not so with the sun. The sun's magnetic polarity flips around about every 11 years or so. And so it's a much more magnetically active system. So the different types of events are not quite the same. Hope that answers the question.
Okay, thank you. Do we have more questions? Yeah, I know it's already 11, so I think people have to go back to work. Okay, well, thank you so much, Jonathan, for hosting this webinar with us. It was really great. Thank you, everyone, for attending. Have a great day.